Last class, we just got a few more topics related to the second refinements for the bridge controller. I want to finish them properly, and then that'll be it. And for your exam, I already spoke about it last Tuesday. I still want to put up together some PDF just to summarize about what we said, but I'll do that pretty soon. But your exam, we still have some time, to get you prepared. Quick reminders. Your lab number 5 is due tonight, midnight, so make sure to submit in time to claim your credits. And tomorrow, maybe early evening or sometime around tomorrow, or maybe Thursday the latest, I'm going to release a solution for lab number 5. You can take a look, especially for the part about the tabular expression or function tables. That's maybe still new to you. And then the review sessions and office hour, they're going to happen maybe not this week, maybe next week. I think it will become a little bit more urgent for you guys to get ready for the exam, maybe next week. So for this week, you may want to handle other stuff. Of course, you can catch up with the lecture as well. I'll definitely give you guys some example questions. I will give them to you by the end of Friday. So you still got about a week to really try them out. You can ask me during the office hour next week or maybe during the review session, either way. All right. So I'll keep you posted about these information. Okay. But I still got 7 p.m. tonight if you want to speak to me, maybe after class. All right, again, data sheets, I already said it. You can definitely do handwriting or whatever you like. Just make sure adhere to the font size requirements. All right? All right, guys, any question? Yeah. So for inference rule, that would be some stuff you will have to include in your data sheets. I may not give that to you, so please. But as I said before, since so many inference rules share very many common hypotheses, you may want to consider be a little bit more creative of putting stuff onto your sheets. You may not just want to put separate inference rule. That might take a lot of space. You may want to say, for example, for invariant preservation, relative deadlock freedom, they share some common hypotheses. Put them in only a single place. And then for the different stuff like a goal, or maybe some additional hypothesis, you can put it somewhere else. Right? Just save some space. Okay. Yeah. We are not going to give you any information during the exam, so please, anything you think you may have to recall during the exam, put it on your data sheets. All right? All right, any other questions? All right, very good. So today, we're going to do a recap, and then there will be about 2 or 3 more important topics. The first 2 will be a little bit more confusing at first, but I'll try to be as clear as possible. Keep emphasizing the big picture for you, but there might be some details you have to maybe digest yourself, maybe after the course. After the class today. All right, anyway, let's now do a quick recap. All right, so last time, let's see over here. All right. So basically, last time we explained about added concreteness into M2. And namely, it's about, for example, in M1, which is relatively more abstract, we got an event called MLL, for example. And MLL over there is keeping track of A, B, and C. And we said that it's not realistic. MLL is supposed to be simulating some car going from the mainland onto the bridge. The driver never keeps track of how many cars are on the bridge and on the island. That's not the driver's job. So this particular event here is not up to the reality in the abstract model. That's why in the M2, the current refinements, we try to split between MLOut and MLTL green. So these are the 2 events that we're considering for the new refinement. So MLTL green is going to somehow get the guards that used to exist in MLOut. That's the short story, right? For the long story, you can go back to that what we talked about last Thursday. And for MLOut in the new refinement model, is only going to check to see whether or not the light is actually green. If it is green, just pass through. If it is not green, stop. All right. So that's an important added concreteness you want to understand first, because all the other discussion items we talk about on Thursday kind of follow from there. All right. All right. So ML out, IR out. So they only look at a traffic light. Again, this will be human behavior for the driver. Okay. On the other hand, for the 2 new events, MLTL green and ILTL green, right? So these will be using, these will be like a computer software, like a sensor or actuator, so they have to keep track of the variable, which make more sense. And by the way, since now in this new refinements, we got new events. Whenever you got new events, you have to worry about the possibility of divergence. That will be the second topic for today. We'll talk about it, okay, in a moment. All right, just remember, whenever you got new events, you have to worry about divergence. And whenever you want to worry about divergence, you have to look at the variance of the system. There will be some interesting variant that we're going to see today. All right, and then we talk about invariant preservation. Okay, nothing special. You guys can just make sure you know how to formulate the invariance, and there'll be some exercise for you to formulate it. And then we introduce some new inference rules, right, over here. Okay, and then let's see. Yeah, so this is actually where we found some motivation to fix our model for M2. So long story short, we start with this invariant preservation proof obligation, and we found that it will end up into something that's unprovable over here. Specifically, if I copy this unprovable sequence into here, that one is saying something like, my model is able to reach a state where both traffic lights are going to be green at the same time, which doesn't make sense. How can you allow cars to go past both ways? And then if I can show you a state in the model where both lights are green, and then 1 is equal to 0. This one also doesn't make sense. It's simply false. So we are basically showing something like a true implies false, which is just false. So that's the contradiction that I have shown to you back on Thursday. All right, so this will be a similar contradiction that we'll see from another invariant preservation proof obligation. You can take a look as well, give a try to see if you're able to also reach to this unprovable sequence. Well, I'll leave that to you. All right, so this page here, I kind of show you the contradiction for this one here. For example, you can see this particular trace is going to lead you to a state where MLTL and ILTL, they are both green. So you can see part of the hypothesis over here, it can be true. Right? So we show that the hypothesis over here can be true by giving you a trace. And then 1 equals 0 is really indicating over here, you can see C is equal to 1. That means car can actually go from here. And also C is equal to 0 at the same time. So that's a contradiction. All right? So for the exact interpretation, you can look for more details from last Thursday, which I also spoke about. So let's say for the exam, if I give you some unprovable sequence like this, for example, how do you actually show it? You will have to look at the hypothesis over here. Are you able to come up with a trace, which I just kind of give to you right away? The trace should really show that it is possible to have these two lights green at the same time. That's basically kind of I gave to you right away. Right? Of course, in the actual exam or in the test, any possible state, you will have to think about what kind of trace can lead to that particular state. That will be something you also need to do. All right, and then we said to fix it, So let me just tell you again. So we got this particular proof obligation, and we got unprovable sequence over here. We got another invariant preservation that's unprovable. We got a similar unprovable sequence. To fix this and this, the way to do that is by introducing a new invariance over here. We're basically saying either light has to be red. It cannot be the case that both are green, which is exactly where the contradiction comes from. All right, so we have introduced this new invariance. And once we have introduced this new invariance, it is important to realize as soon as you have added some new invariance, you basically somehow add more hypotheses into the proof sequence, basically, right? So if you revisit the proof tree over here, you can see we try to add the new invariance everywhere throughout, right? And then when we go back to the sequence that was originally unprovable, now given this new invariance as a new hypothesis, we are able to discharge it, right? I kind of show you two possible approaches to really go. But if you think about another one, feel free to try, and then I can verify for you. All right, so the conclusion is, after adding this particular invariance, we are able to discharge this proof obligation, and also this proof obligation. And this one here will be for you to do some exercise for. All right. All right, so that's basically what we did last time. It's mainly about to interpret the unprovable sequence and see how we can fix the model to really get them provable. All right, question? All right. If no, let's now move on. And we're going to keep fixing the model until it is going to pass all the proof obligation for the correctness criteria for refinements. Okay, so to start with, let's do something light. So we talk about the new events, MLTL green and also ILTL green. And also let me remind you, let me go over some slides. I think that'll be clearer. So the new invariance that we have just added is invariant 25, right? That one there, as I just said, is about the two lights cannot be green at the same time, all right, over here. And you also want to think about the consequence of that. So the slide tells you that if you have added this particular new invariance, how many more proof obligation are we going to need to discharge? Now it gives you some number here, 6 times 1. All right, so that's something you have to somehow work out in your mind why it is the case. All right, so think about over here, we have added invariant 25, which is over here. I'll show to you again. This one here, that's a new invariance, right? Since it's a new invariance, we want to make sure every event in the model is able to preserve it. And then that one there is going to be, so we talk about 1. So this is the new invariance. Also multiply by 6. So the 6 over here are all the events we have in M2. So very quickly, we got ML out, we got ML in, we got IL out, we got IL in, and also we got ML, TL green. These are the new events. Also we got IL, TL green. Okay, that's an important observation. So if I only tell you that we have added 1 new event into the model, you should really kind of click right away. How many more proof obligation is going to impact, right? We're going to get additional 6. Okay, 4 of them are to do with the old events. 2 of them are to do with the new events. And something for a look ahead. It turns out we have to look at these events and this event more closely as we talk about divergence. Okay, sorry, not divergence, something else. Okay, but we're going to look at these 2 events more closely very soon. Okay, but for now, it is good. All right, just make sure you understand about the 1 times 6 on the slides. All right, and then 2 of them will be MLTL green, ILTL green, right? And these 2 will be something that we want to preserve. Let me just show you very briefly, right? The proof is going to be up to you, but they should be relatively straightforward to actually discharge. But before that, you want to make sure you add 2 actions over here. Okay, I'll show to you. So this is something I will tell you right away. Of course, if you simply try to, let's formulate proof obligation first, and then I'll talk about the added action. For example, this is the new events, MLTL green, invariant 25. And let me remind you what it is. Invariant 25 is MLTL equals red, or ILTL equals red, right? Quick reminder. And how do we state the proof obligation? So these are all the hypotheses over here. For example, you can see the axiom over here, all the axiom, and also all the, one thing to note. I'll make it a little bit larger here. You can see the naming convention here. 0 over here. Also, you can see the 1 here. So we are really accumulating all the constraints we have developed so far from models 0, 1, and 2. And that's 2 over here. So you can see these are the invariants from M0. And these are the invariants from M1. And these are the invariants from N2. All right, so put them there. Okay. Of course, you can look at the model and make sure they are there, right? So this one here, we don't need to write them out from scratch. And if you also recall the invariant preservation proof obligation, not only that we got to put all the invariants together, also we need to put a concrete guard for the events, right? So since we are talking about MLTL green, so what we will put is we're going to put the concrete guards. Concrete guard of MLTL green. All right, so which will be exactly here. MLTL green is here, that's its guard. And when you do the exercise for ILTL green, of course, you got to include this one instead. I'll leave the exercise to you. And that's the only hypothesis I need to add. So I would say MLTL equals red, A plus B less than D, and also C equals 0. Right? So that's the complete hypothesis for that proof obligation. And then the turnstile over here. Right? And then we're going to put something here. That would be the corresponding invariance in the post states. Right? And since we are talking about invariant 2.5, invariant 2.5 is over here. We want to make sure that one there is satisfied at the post states. So that would be MLTL prime equals red, or ILTL prime equals red. And the way to simplify, let's do it together, since this might be the last chance we're going to do it in the class. So here we're going to look at the before-after predicate. All right. So the before-after predicate depends on the action. All right. This is something you want to note. Up to now, we didn't really have this added action. If you only include the original action that we introduced a few lectures ago, we only turn the MLTL to be green. This turns out to be not sufficient to really prove the sequence over here. So we need to add this particular action, which is to say, if you want to turn MLTL to be green, over here, you must also turn the opposite light, ILTL, to be red at the same time. Okay, so that's something you guys actually kind of observe anyway from last time. So now, here you go. All right, and symmetrically, when you try to turn this light to be green over here, this one has to be turned red, right, symmetrically. So this added action is to make sure this sequence over here is provable. All right, so let's now simplify this. And this one tells you MLTL prime equals green, and also ILTL prime equals red. MLTL prime equals green, and also ILTL prime equals red. All right. So what you will get over here would be something like green equals red, or red equals red. And which can just be simplified to true. Agree? Because, for example, by arithmetic, this one here is already true. True or anything overall is going to be true. And then that's it. You can apply the relevant inference rule to prove it right away. All right? But without this added action, you will not be able to do it. Okay? Your exercise will be to really try to specify the other one that's relevant to invariant 2.5, ILTL green. And then try to prove it. It might just be as trivial as what I have just shown to you. All right? Any question about this one here? Okay, hopefully it's still pretty light, right? All right, so this one's done. And then we're going to go further. Okay, here comes something a little bit trickier. So let's now do the following one, and then we'll take a short break. All right, let's now do something slightly heavier. And for that one there, I want to give you a little bit of summary on one page so you will see. Otherwise, the naming there, even though it's quite systematic, but since we're doing different invariants at different proof obligation, you might easily get confused. So let me summarize that in a new page. And then we'll go ahead and do it. Okay. So far, let me just remind you from Thursday, right? Let me make some reference. So what we have discussed, so that's back on Thursday, right? Last week. So you can refer to the lecture later if necessary. We discussed two proof obligation. Okay, we actually got ML out, and that one there has to do with invariant 2,4. And then I'll list them in a moment, just to make it self-contained. Give me a moment. Also, we try to prove IR out, invariant 2,3, and also invariant preservation. Okay. And let me now put the actual invariants over here. The invariant 2,3, so you don't need to go back to lookup. So MLTL equals green implies A plus B less than D, and also C equals 0. Also, we got invariant 2,4. That one is about ILTL, the other end of the bridge. ILTL equals green. That implies also the capacity and then safety. B larger than 0 and A equals 0. All right, that's just a reference point for you. If you think about how many, if we want to make sure, for example, the preservation of these two invariants, we want to make sure these two invariants are preserved by two events. How many proof obligation do we need in total? 2 times 2. We need 4. So last week on Thursday we discussed 2 of them. Today we're going to discuss another 2. Okay, that's kind of the big picture. All right. All right, just very quickly. So if you recall, so this one here has more to do with. Okay, so this one has more to do with ILTL, right? 2,4 over here. ILTL equals green. And then what we discussed last time was more about the contradiction of the C and C being 0 and 1, right? Which I just recap in the beginning. A equals 0. And this one here, part of it is about C being equal to 0. That's MLTL equals green implies, you can see C equals 0. This part here we already have discussed last time. And in order to make these two provable, we added the invariance 2,5. Okay, so this one already discussed. And today we're going to discuss the other two, which will be ML out but invariant 2,3. And also IR out but invariant 2,4. Right, so the missing 2. And I will briefly recap about what we're going to see. And then we're going to go ahead and see the proof obligation. And something we're going to discuss today. To discuss today will be the other 2. So it will be the same event, ML out, but now rather than 2,4, it's going to be 2,3. Invariant 2,3, and then invariant preservation. And also we got IR out. Also we got invariant 2,4. Right, you can see 2,4 versus 2,3, right, from last time. All right, so that's for today. And let's now have some look ahead about the property we're going to focus on. So last time we focused more on the safety aspect. All right, for last time. Today we're going to focus more on the other part of the conjunction in the consequence. We're going to look at more about the capacity aspect. Okay? So think about these are more to do with safety. And today we're going to see something that's more to do with capacity. Okay, so for this one over here, it's going to be something like MLTL equals green implies A plus B less than D. And this one here is more about ILTL equals green implies B larger than 0. All right. So this one here and this one here, they have more to do with capacity. So we kind of separate the discussion. All right. So these two, we're going to talk about it in the next maybe 15 minutes or so, and we'll take a short break. All right. All right. Any question here so far? We're good. All right. So what we'll do is we're going to somehow formulate the proof obligation. All right. Let's now take a look at, let me just double check. Yep. So this one here, for example, this one here. Okay, we're going to formulate the proof obligation here. Okay, exactly here. All right, that one there, as you can see, it has to do with invariant 2, 3, and also ML out, right? So these are the two. Okay. And this is the complete proof obligation. That's something you can definitely double check. What I will actually draw your attention to will be, one thing to see is, since we're talking about ML out, so ML out, so we talk about its guard, MLTL green, and MLTL green. So we are really talking about when MLTL is actually green, what's going to happen, right? That's the context for discussion. And then here, the goal over here is to say, when MLTL is actually green, and then here we say something like A plus 1. All right? If you look at the pattern here, okay, that's worth your attention for sure. If you look at just this one here. Oh, you know what? Let me make it even narrower. Look at this part over here. Just this part. All right? Just this part here. First of all, we got MLTL green, which matches the guard for ML out. That means we are really talking about where ML out is actually enabled. That's the context we're talking about. All right? And somehow we want to be sure somehow A plus 1 plus B is strictly less than D. And if you look, let's now think a little bit backwards. If you look at the action for ML out, right? So that one corresponds to A prime equals A plus 1, which means if I allow ML out to really occur, that means I got one additional car onto the bridge. That's why the counter A should be incremented. All right? So that one is to say here A plus 1 really represents the post states of ML out. Okay, A plus 1 over here is really the post states of ML out, in which case A prime equals A plus 1. So this one is to say, I want to make sure after the additional car has gone onto the bridge from the island because they got a green light, the capacity constraint, which is part of the invariance over here, is still preserved. That's basically how you interpret that. All right? That's the thing I want to point out too. Of course, to formulate the proof obligation itself, you can definitely do it. Right? That's something, no surprise to what we did earlier. And it will be up to your exercise to try it out the other one. Okay? So this one here is similar. So the other context will be when we talk about IL out. IL out is going to be going this way. Over here. So we want to make sure when the line here is actually green. And then we allow IL out to really go through by allowing one additional car into the bridge. In that way, you can see C will be equal to C plus 1. Right? So you got to make sure the constraint, sorry, let me say it again. For this one here, let me write it out. IL out over here. The main thing to look at will be B. Because we know that B prime equals B minus 1. If you allowed IL out to actually occur, that means one of the car from the island is not going to go onto the bridge. So that's why B will be decremented. And the invariant tells you that B must be always larger than 0. So you got to make sure in the post states for the IO out, the B will still be larger than 0. So when you do the exercise, you'll realize the constraint we want to prove will be B minus 1 should be larger than 0 after the car has gone onto the bridge from the island. So once you do the exercise, you will see exactly that proof obligation, right? I'll just give you some guidance when you do the exercise, just like this one here. All right, any question? Okay, that's good. So we have formulated the invariance, and it turns out it's unprovable. That means we got to do some further work about fixing the model. Before that, let's now take a look at to see exactly how it's not going to be unprovable. Pretty much what I said already. Okay. So this is the proof obligation I showed to you exactly here. Okay, I just moved it here. And then you can follow the entire proof tree, right? So you can see we're using some of the new inference rule that we spoke about last Thursday. You can definitely take a look to see how they apply. And the unprovable sequence is over here. Okay, that's the one. Okay, let's now analyze it quickly. So this one here is unprovable. This one here. Okay. And let me write it down here. So it is unprovable. That one tells you A plus B less than D, and also C equals 0, and also MLTL equals green. That entails A plus 1 plus B less than D. All right, so that's the unprovable sequence. And we're going to analyze it in the next page to gain some insights from there and see how we can fix the model. So the hypothesis is the lights over here is actually green. So we might allow ML out to actually go through. But somehow we are not able to show that A plus 1, which will be the car gone to the bridge. So that means A plus 1. Plus B less than D cannot be proved. Question? Here? That should be implication R. This one here? This one here? Could be. That one looks like modus ponens, right? Yeah, you could be right. That could be a typo. Okay, it's yeah, I agree. Thank you. I'll try to fix it in both the slides and also the notes. That's awesome. That's great. All right. Yeah, and this unprovable sequence over here, we're going to look at that in the next page. All right. Very nice. Okay, let me just make sure this is not good. Okay. Okay, let's now take a look at this unprovable sequence over here. All right. Let's now visualize them even more closely. Right? We'll look at this in a moment. Okay. So if you look at the hypothesis over here, we say that number one, MLTL equals green. MLTL equals green. And the fact that it is green tells you that ML out is enabled. Okay, right away. Because you can see for ML out, it has the guard MLTL equals green, right? That's something you can see right away. That one tells you ML out is enabled. Because it is enabled, so it might occur. So we want to make sure when it occurs, the invariant should be preserved. But it doesn't seem to be the case that's provable. So let's see. So it's saying that given that the light is green over here, and also the invariance, which is over here, invariant 2, 3, right? That's the one that's unprovable. So A plus B less than D is the case over here. And also C equal to 0. That means there's nothing coming to here. So safety is not really our focus here. It has been proved somewhere else. Okay. So what I want you to focus on would be this part over here and this part over here. All right. So that part there cannot be proved, which makes sense. So if you think about like this, if you got, for example, a plus b in general, if you got x less than y, does that mean x plus 1 also less than y? Apparently not. All right? Because, for example, not true in general. For example, let's say 3 less than 4, but 3 plus 1 less than 4 is not true anymore. Right? That's a very easy counter example to find. Right? For x and y. So that's why this part over here is not provable. And the insight is, when you say ML out is going to occur, you want to make sure A plus B less than D somehow is not really large enough so that after this additional car goes into the breach, it's going to violate exactly this. So for example, you want to make sure if I tell you that X is less than Y, that's fine, but X for X plus 1 less than Y, X cannot be equal to Y minus 1. Right? That's something you want to think about, because when X currently, if it's already reaching that maximum possible that's less than Y, in that way, after adding 1 to it, you get exactly Y, which is going to break this streak less than. All right? So that's the analogy you want to maybe think about aside. What does that tell us? That tells us right now, our ML out over here may have to be somehow be split into two versions. We want to make sure some ML outs, after adding this additional car into the breach, the green lights may maintain if we have not exceeded the limits. But as soon as the car actually gone onto the breach, we are just reaching that exactly last car that can be entered into the breach. We want to turn the light to be red. So there are two versions over here. All right. So that's why I'm going to talk about some split of the cases over here. All right. So we're going to focus on this condition here. So we look at this condition here, A plus 1 plus B less than D, especially for the A plus 1. Can think about this one is ML out allowing one new car onto the breach. Right? So we're going to see exactly how this condition is going to evaluate. Right? Because as soon as it becomes false, we want to make sure the light is turned red. So no more cars should really go into the breach. Yeah, question. Say it again, sorry. When we are proving model here.
Yeah, this like M2, M1, sorry, M1. We had the same sequence and we were able to prove it using linking variable, like A plus B plus C is equal to and C is 0.
Yeah.
So why cannot we use that here?
No, this is actually a different one. So here, so think about where this comes from. This unprovable sequence over here actually comes from this proof obligation, right? Sorry, say it again. You mean we have?
We also have the same hypothesis we have in M2, like the ones that we had in M1, right? So we can just use the same ones to prove.
No, that one would not be shown as provable, actually. You're talking about A plus B plus C equals D? Okay, how about this? For this one, show it to me, maybe after class, what your proof is. But that one is not going to help. Because remember what we did earlier? We actually included all the possible invariants from all the models over here, from 0, 1, and 2. But somehow they are not going to help. No. But why don't you show it to me, maybe after class? All right? Okay. Anyway, so we got this unprovable sequence over here. And then we are now trying to interpret that. And it turns out the way to really fix this one is to look at two groups over here. So let's now take a look at some example here. Let's say the maximum number of cars that's allowed in, so remember A plus B must be strictly less than D, right? So let's say they must be strictly less than 3. Okay, just say for example. What we want to do is, given that D is equal to 3, we want to look at the different combination of A and B. So here I simply enumerate all the possible value for A and B over here. You can check that it's exhaustive for A and B. So let me tell you the conclusion right away. We can somehow split them into two groups. This is group number 1. All right, and this is group number 2. All right, somehow group number 1 is going to make sure A plus 1, by allowing one extra car, you can still satisfy that safety constraint, capacity constraint. Okay. So group number 1 has the fall. So that means A plus 1 plus B not equal to D. Right? You can check that. For example, you can see here I got A plus 1, which will be 1 plus 0. I haven't really reached the maximum just yet. If I have reached that, that means I need to turn the light to be red right away. So this one tells me no need to turn MLTL to red right away. All right, that's important. Okay, so we're basically saying whenever ML out is actually enabled, you will allow for one more car onto the bridge. That's okay. However, as soon as that particular car has gone onto the bridge, there will be two possible cases. Either the lights of MLTL can remain green, meaning that we can allow just another car coming in. But there will be other cases where maybe we have just reached to the condition where if we allow one more car in, we're going to exceed the capacity. In that case, we have to turn the light red right away. All right, so that's the main insight. All right, so this second group over here will be A plus 1 plus B reaches the maximum capacity. All right, so that means if we allow the extra car by ML out onto the bridge, we should turn the MLTL to red right away. Okay, let's write this down and I'll do a recap. This one tells us we need to turn MLTL to red right away. Okay, so let's now recap. Given this unprovable sequence over here, which is really about if I have the capacity constraint satisfied given that, but if I try to add one more car, there's no guarantee if I have the constraint satisfied. The way to really do that is to think about the lights. Because if MLTL is really green, I can keep allowing cars to go into the bridge. So I gotta stop that at some point. So the way to do that is we're gonna kind of split the ML out. Think about for ML out, we're going to split that into two cases, right? Case number 1 and case number 2, which we're going to see in the next page. For case number 1, it will be such that by adding a new car into the bridge, we haven't really reached the maximum capacity just yet. In that case, MLTL can remain to be green. All right? And the second case is such that after allowing the extra car onto the bridge, we're going to reach the maximum capacity. In that way, doing ML out is going to be not good because it's going to exceed the capacity. So we have to turn turn this light here red right away. Okay, so these are the two cases. And the way to really reflect these two insights is to really modify the events, which you're going to see in the next page. All right. All right. Any questions about this? Anything that's not clear? Feel free to ask me to clarify. This one's tricky. All right. All right. So now let's take a look. So the way to really address this is you can look at this constraint over here and this constraint over here. These two are exactly the two conditions I spoke about. We're just using them as the new guards for the events. All right. So what we'll do is I'm going to talk about this one over here. So what we're doing is think about in M1 and also think about in M2. So for M1, we got ML out. And also we got IL out. All right. And for ML out, we actually got in M2, we're going to split that into ML out 1 and also ML out 2. And for this one here, we're going to split that into two cases. IL out 1 and also IL out 2. That's the way to fix the model, which is kind of a new, right? We just have to make sure we distinguish between this ML out here. We haven't really reached the maximum capacity. So the MLTL can remain green. But as soon as we reach the capacity over here, we have to make sure we turn the red. All right? That's really the fix. So these two are related. As soon as the capacity limits is reached, turn MLTL to red. Okay, one more illustration. Think about this one here. Let's say MLTL currently is green. And the idea would be we will allow ML out 1 to actually occur for as many times as we like until we reach this particular limits. As soon as this one is really reached, and we're going to expect ML out 2 to really occur. In which case, once this condition is really satisfied, this one here will be disabled. All right? So another insight over here, which also disable ML out 1. And the ML out 2 part of it is also to turn the light to be red. Okay, so you can expect we got a series of ML out 1 and the light will remain green. As soon as we got a first occurrence of ML out, we're going to turn the light red. That's how we can be sure the capacity limit is respected. It's never exceeded. All right, this one's tricky, right? But it's not too bad. It's to say, once we have seen that unprovable sequence over here, we decided that we're going to split into two different versions of ML out. And the main thing is, as soon as the capacity limit has reached, we should really turn the light red right away. All right, this one here is going to be just the same, right? That one there, you can give a try, right, to figure out exactly what's happening here, right? You can see ILTL at some point should also be turned red symmetrically. All right, any questions about this? Okay, that's good. So why don't we take a short break, and then after the break, I'll talk about divergence. That'll be the second one that's important. All right, let's take a short break. Okay, so before the break, we spoke about splitting ML out and IL out. You can think about it a little bit more. You can ask me again, maybe during the office hour, or maybe in the review session, we can revisit again. All right, so now the next one will be almost the final topic we need to talk about this model here, which is about divergence and some variance, right? The conclusion is, well, mini conclusion. Somehow the current M2 may lifelock or may diverge. Okay? And let me remind you very quickly, whenever we talk about lifelock, we only consider infinite interleaving of new events. Okay, infinite interleaving of the new events. Interleaving of new events only. If you got infinite interleaving of the old event, it's not lifelock. It's completely okay. Right, so this one is just for you to recall the definition for lifelock. Okay, new events. That's important. And you can see MLTL green and ILTL green. They are only to change the traffic lights. All right. And I'm going to give you this trace right away. You can take a look at the detail. But starting from this point over here, basically after this leading trace over here, starting from this point, we are going to enter some interleaving of new events. All right. So after this one here, so this will be the starting point of lifelock. Because starting from this point here, it is possible to basically have the following sequence. We are going to turn ILTL green, and then MLTL green, and then ILTL green, MLTL green. Basically, the two lights are simply flashing. All right? That's basically what's going to happen. That's a lifelock because the driver simply wouldn't know what to do, apparently. All right? But you can somehow see exactly why this can happen. If you look at the guards for these two, right? For example, MLTL green has to do with A plus B less than D. So if you look at all these, A plus B less than D, that's for sure. Right? You can see A plus B is 1, 1, and 1, strictly less than D, right? So you can see this part here is true. And also MLTL is actually red before you turn it green. So MLTL is actually red before you turn it green, okay? And etc. And you can also double check to see all the states over here also satisfy the guard for ILTL green. So this is how the lifelock can start happening. Right, so when you study for this part here, number one, convince yourself that this particular trace is currently allowed by the model here, specifically these two events. If there's such a trace for such infinite interleaving of the new events, that means the current model diverges. Okay, let's now write down this review over here, and then we'll see how we can solve it. Okay. The current M2 diverges because there is one valid trace of infinite interleaving of the new events. All right, so that's something you want to look at. Okay, diverges. Okay, so we're good with this trace. You can take a look offline and try to see exactly how it will be reflected on the diagram as well, right? You can take a look. And what I want to focus on, hopefully in the next 10 to 15 minutes, is to really try to see how we can prevent the lifelock. So there are two things I will hope to talk about. Number one, how can we prevent it? Number two, how do we prove that we have prevented that, the lifelock? In order to prevent it, we're going to introduce two variables. In order to prove that there's no lifelock, we got to look at the variance, right? Two things. Okay, that's now, I think the first thing is more important, right? So we're going to get two variables over here. So one is called ML pass. The other one is called IL pass. Okay, two variables. And let's now take a look at what they really mean. NL pass is going to be either 1 or 0, like a true or false. When ML pass is actually true or it is equal to 1, that means ever since MLTL, the traffic light from the mainland side has been turned green, there has been at least one car exited from the mainland. All right, that's a definition. If it is not the case, it's going to be 0. All right, you can revisit this definition later, but I'm gonna illustrate to you how this can be used to really regulate the traffic lights. Similarly, for IL pass, which is the other new variable we are introducing, this one here has got similar thing. It will be either 1 or 0. If it is equal to 1, that means ever since the traffic light from the island side has been turned green, there is at least one car that has passed. And we're going to use these two to really control the enableness of MLTL green and ILTL green. All right, so these are the two variables. All right, let's now do some annotation on the next page. So that'll be the main thing. And the rest will be something that you can also try it out yourself. So now I put all the relevant events all together, right? Now we're going to focus on understanding about, you can see we have some IL pass over here. We got ML pass and etc. Okay. So these are the two split events that we spoke about before the break, and ILL, ILL1, ILL2. Okay. And MLTL green, ILTL green. So now we're going to see exactly how to understand the behavior. Let's start with ML pass. Okay. So now what you want to do is, let's now circle that. As soon as we actually got MLTL green to be executed, what? Think about it happens. So we got ML pass over here. I want you to look at this one here, ML pass, and also ML pass over here. Also ML pass over here. So these are the three places where ML pass got assigned some value. As soon as the light has been turned green, no car has passed just yet. In that case, ML pass will just be 0. That's according to the definition. Okay. So this one here is going to be, since MLTL turn green, no car has passed. Right? If you go back to the slide for the definition, that's exactly the case. Right? No car has passed rather than at least one. That's why it's 0. And very important to see. Remember, the very reason for divergence is after MLTL green, we are able to have ILTL green right away. So ML pass is going to make sure once it is turned to some value, it's going to also disable the other new events. That's the main critical thing. Right? So if I look at ML pass is actually 0 over here, it's going to disable the guard for ILTL green right away. All right. So you want to also look at this one over here. This one is going to disable the guard for ILTL green. So this disabling effects is the critical highlights about how we can prevent Livelock. All right, this is important. Okay, let me do a very quick recap. So 1, 2, and 3. So these are the three places where we are trying to manipulate ML pass, the variable over here. And then we are saying that when we set this one to be 0, that simply means after MLTL has been turned green because of this event occurs. No car has just passed yet. Car will only pass once we got ML out, either 1 or ML2. That's something we'll do in a moment. So since there's no car has passed yet, we set this one to be 0. At the same time, this is going to cause the guard over here to evaluate to false, which will effectively disable these new events over here. That's how we prevent divergence. So I'm going to do some quick tracing over here to see exactly how that's going to occur. All right, so now let's now focus on this value over here. Right? You can see both of them are going to set it to be 1. All right, so because MLL1 and MLL2, they're both going to increment A by 1. That means some new car has passed after the light has been turned green. That's exactly the definition for why they should be 1. Okay, since MLTL turn green, at least 1, larger than or equal to 1 cars passed. Over here. All right, just understand how the value for ML pass is really changed from 0 to 1, and then how it will disable the other new event. That's the main thing. All right, that's how we prevent divergence. And just to keep the diagram relatively clean, what you're going to do is think about for IL pass. All right, for that, I'm just going to highlight what you should really look at. For IL pass, you can circle a box IL pass over here, and also IL pass over here. The description will be just symmetric over here, and also over here. Okay, I'll describe that very quickly. When IL pass is assigned to 0, that means after ILTL has been turned green, no car has passed just yet from the island onto the bridge, which will effectively disable the other new events. And then at the same time, once we got either ILL1 or ILL2, we're going to increment the number of cars onto the bridge. In that way, there's at least 1 car passing onto the bridge after the light has been turned green. So that's why we'll set the 1 to IL pass. Similar description. Right? So when you look at the use of ML pass and also IL pass, they're used in a very similar way. So just follow through my description for ML pass and do the same for IL pass. Okay. All right. Any question here about these 2 variables? Okay. Again, we use these 2 variables to regulate the traffic light and make sure we don't have any divergence. So what we should do now is to fill out this table here. Right? So how do we fill it out? What we'll do is we're going to follow through this particular trace over here, right? You can look at each event over here. Okay, I'll let you double check the value. But when we go for this particular trace, it's going to illustrate to us divergence is no longer possible. Okay, I'm going to fill out the value exactly. Okay, let's say for example, initially we are simply going to get 1, 1 because we want to make sure MLTL green and ILTL green are both enabled. So either one can occur. But as soon as the very first one occurs, the other one is disabled at the same time. So there's no danger over here. All right? So this one here is the initial states. Both new events enabled. Okay, so whichever that happened the first, the other one is going to be disabled, as we said. All right, so now just trace one of them to show to you. MLTL green is going to set ML pass to be 0, and IL pass doesn't change, so it remains to be 1. So we're going to get 0 here, and also 1 here. And as soon as we got 0 over here, that tells us the other new events is disabled. IL, TL, green. So this is going to make sure what we had earlier after MLTL green, we're still able to have ILTL green. It's no longer possible. So we are no longer able to have Livelock. Okay, you can do a similar tracing for these. And let me just give you the numbers here. So we got 1, 1, 1, 1, 1, 1. Simply because whenever you got MLL1 or ILL1, we don't really change the value, right? They're just assigned to be 1. Okay, 1, 1. And once we get to ILTL green over here, if we want it to occur, it's going to make ML pass to be 1. At the same time, it's going to disable the other events symmetrically. Right? We got 1, 0. All right, if you keep tracing, you're going to get 1, 1, 1, 1, 1, 1, 1, 1. All right, so the 2 rows to really pay attention to will be these 2. 1 here and 2 over here. All right, and the critical insight is when you actually try, when one of the green light events occur, the other one is gonna be disabled right away. Okay, so divergence is no longer possible. All right, any question? Okay, so your focus point when study this page here is number one, to understand how the two variables are being manipulated in a symmetric way. And when you do the tracing, try to see how the value for one of them becoming 0 is going to disable the other new events. Right? So these are the critical things to watch out for. So we basically have effectively shown that the Livelock is no longer possible, but we want to formally prove it. To prove it, we need something called variance, which we spoke about in M1. If you recall, the M1 is like a 2 times A plus B, right? Because we got a different scenario for divergence. But for now, these two variables can be used as the as the variance condition for M2, right? So it's a different variance because we're talking about different model. ML pass and IL pass. This part over here is the tracing that we just discussed over here, right? So what I will do is I'm going to add on top to see how the variant value is going to change and plot the graph very quickly to show to you, right? It's going to reaffirm the pattern that we spoke about earlier when we talk about M1. Okay, so once we plotted this graph, we're almost done. Okay, let's now do that quickly. So you can see ML pass, IL pass, and the variant value will be the addition, the sum of them. So 1 plus 1 will be 2, and then 1, 2, 2, 2, 2, 1, 2, 2, 2, and 2. As you can see, the variant values seem to be either 1 or 2. And let's see exactly how that value is going to change. Specifically, let's pay more attention to 1 here and also 1 here. Okay? Notice one thing. The variant value decreases from 2 to 1 because we got occurrence of the new events. From 2 to 1 because we got the occurrence of the new events. Whereas when we simply got the old events, we either go from 1 to 2, increasing it, or we simply have the value from 2 to 2. Doesn't change. That really confirms the pattern that we said earlier. But let's now plot the graph very quickly. So here we got the variance, all right? And we know the value can either be 1 or 2. It's either 1 or 2. Okay? So we got 2 here. So we got 2 here after init. And then we got 1. And then we got 2. 1, 2, 3, 4. 1, 2, 3, and 4. And then we go back to 1. And then we go to 1, 2, 3, 4. All right, let's now try to connect the dots. So I basically got this one here and this one here. And it remained the same for a while. And then it will drop. And then it will increase again. And then it will remain the same. Right? That will correspond to all the events over here, right? And let's now summarize the pattern over here. So when we go down, that's really the definition for the new events. Whenever the new events occur, one of the proof obligation is the variant value should strictly decrease. So you got here, also you got here, right? So you can see this one is because we got MLTL green. And here we got ILTL green. Okay? And then the rest. So you go up, also you go the same, also you go up or you go the same. It's basically all the other O events over here, right? And I'll also confirm what we said earlier. For the O events, you either increase the variant value or maintain that to be the same. All right, so all these will be the O events. All right, this one as well. All right, so that's a plot, right? And that's only some informal confirmation. To really show this formally, we need to prove it. Okay, so we're going to formulate the proof obligation for variance. And you can definitely go back to the slide and see how we did it for model 1. One of them is about the variant here. That's the most critical one. The other one is about net, right? The variant value should be always a natural number. Let's talk about this one here. And do you guys remember what this really means? If you know, you may want to put it on your data sheets, right? It's a critical one, all right? Very quick recap about this one here. This one simply tells you, think about this one here is the post value of variance, post states. The post state value of variance versus the pre-state value, because it should be strictly decreasing. So that's the pre-state value of the variance. All right. And then what we want to really work out is how do we arrive in this particular goal over here. Let me talk about it very quickly. Okay. Since the variant is over here. Okay, so maybe put a star here. So we want to make sure ML pass in the post states prime, right? You can see the post state here. Also plus IL pass prime should be strictly less than ML pass plus IL pass. Right, you can see this part here is the post states. And this part over here is the pre-states, right? But how do we figure out the post states? We have to look at the before-after predicates, which will be, since we talk about MLTL green. MLTL green, so we got to look at the action over there. The only thing we got is ML pass. So this one tells you the before-after predicate should be ML pass prime equals 0, and since we don't really measure IL pass, so it should remain the same. So let's do the replacement. So this one here is going to be 0. That's the 0 you see over here. And this one should be IL pass. That is the IL pass you see here. All right, so that's how you work out. Just want to show to you so you kind of remember. And once you understand about this, you can see you got a very huge chunk of hypotheses. You don't necessarily need all of them, but it'll be exercise for you to see how you can prove it using monotonicity. Any question? All right, so we have done divergence analysis. We started from the problematic trace, talk about how you can use two variables, IL pass, ML pass, to regulate the traffic lights. And then we talk about the pattern for variance, and we talk about formulation of the proof obligation, right? Give me maybe 2 minutes, and then we are done. All right, so the next one will be about relative Deloff freedom. And that's something we spoke about also for M1. So the idea will be just the same, right? So what I want to show you is this part over here will be the disjunction of all the abstract guards. So for the abstract guard, sorry, let me use a different color. That might be easier. So the abstract guards is going to be all in M1. So you're going to look at abstract guards, and put them all together. Right? If you recall the definition for relative Deloff freedom, it should be abstract guards implies the concrete guards. For the reasoning, you can refer to the lecture earlier. And that should imply the concrete guards, which should be for M2. So over here, over here, over here, and over here, right? That's all you got over here. And you can definitely see the correspondence here, which I put down already for you. Right? You can see the annotation. It's all there. And how do you prove this? This is going to be a challenging proof. Okay? So for you guys to do it, I give you some guidance here. You start with this one here. Somehow, you should be able to go from here into some intermediate sequence. So I give you 3. Think about that's intermediate sequence 1, intermediate sequence number 2, and also intermediate sequence number 3. So from here to here, and also from here to here, and also from here to here, you will just need some lists of steps using the inference rule that we have talked about so far in the course. Right? So that would be something that's up to you to really prove the relative data freedom. It's doable, but you will have to try. Yep, so nothing else to say about data freedom. Everything has been said when we talk about the M1. So you just gotta recall how to formulate the proof obligation and how you can actually formulate it. Right, so this will be like a summary of everything by putting M1 and M2 together. All right, so let me just use 1 minute to recap very quickly. So we have basically talked about the complete 2 refinements for bridge controller. And then, so this case study here plus the math review will be covered in your exam. Right? I think we covered quite many stuff in this course. All right. And for those of you who might be taking 4315 again next term, then I will see you. Maybe see almost all of you, right? I hope. That'll be great. All right, as I said, I'll reach out to you about the review session and the office hour. Review the stuff. If you got any other question, I still got 7 p.m. today. All right, thank you so much.